As humans, we have always been interested in the origins of our species. Where do we come from? Who were we before? And how did these ancestors of ours behave? Astrophysicists, in a similar way, try to probe the very beginnings of our universe. Today's scientists are trying to uncover the mysteries of the earliest stars in the universe, the ancestors of our Sun, using an exciting new type of astronomy. Scientists have finally unlocked a whole new way of looking at the universe, and it's all thanks to Albert Einstein. In 1915, Einstein debuted his theory of general relativity, which revolutionized our understanding of space and time. In fact, it says that space and time are not separate, but form a four-dimensional space-time through which all objects in the universe move. Now, scientists have been trying to experimentally prove or disprove this theory for a century, yet time and again it has stood up to scrutiny and has spawned entire new fields of research, which have given us amazing technologies. You can thank Einstein for the GPS in your smartphone. Now, scientists are testing the final prediction of general relativity, that is, the existence of gravitational waves. Einstein predicted that when two objects of vast mass interact in the universe, they create gravitational waves which radiate away at the speed of light, much like ripples on a pond radiating away from a large splash. The most energetic example of this is two black holes inspiraling and finally merging. It was another physicist, Carl Schwarzschild, who predicted the existence of black holes. In 1916, after studying Einstein's theory, Schwarzschild derived an exact solution for the equations of general relativity. This solution predicted the existence of spheres of matter so densely packed together that not even light itself could escape their gravitational pull. These spheres in Einstein's four-dimensional space-time are like a hole in that space-time, a hole into which anything that falls can never make it out again. Thus, they are known as black holes. When two relatively small black holes circle towards one another, finally collide and merge, they release the energy equivalent of 10,000 exploding stars. But they release this energy in the form of gravitational waves, which until now was undetectable by other forms of astronomy. These systems are called binary black hole pairs, and now that we have a way of studying them, they'll be able to tell us amazing things about the early universe that we could only theorize about until now. These systems are like ticking time bombs. Their timers are set when they're first born, and then when they finally circle towards one another and merge and release all that energy, it carries with it information about the system and about the universe in which they were born. In the early stages of the universe, dark matter caused the primordial hydrogen and helium to clump together into small lumps. These then drew more and more matter onto themselves and grew until they became vast clouds with masses up to 100,000 times that of our Sun. These enormous clouds then collapsed down into clusters of hundreds to thousands of massive stars. These massive stars burnt through their fuel quickly and collapsed, creating black holes and simultaneously letting off vast amounts of energy in the form of supernova explosions. These explosions hurled newly formed heavier elements such as carbon, nitrogen and oxygen out into the young universe, dispersing these elements into the clouds that would form the next generation of stars. All this happened over 13 billion years ago in the early stages of the universe's life. Move 9 billion years down the track when our Sun was born, and these heavy elements are the seeds that form the planets of the solar system, and specifically our Earth. This means that those first enormous stars weren't only the ancestors of our Sun, but of the planet we call home as well. There are three ways that these binary black hole pairs form that interest scientists. When a pair of black holes orbit each other, they lose energy as gravitational waves, slowly spiraling inwards, picking up speed, and then finally merging. So we want to study the ones that will merge at a time when the gravitational waves can reach us now, here on Earth. Each binary has a timer setting. How far apart they are from each other when they are born determines when the merger will happen. So say we have a black hole binary pair that formed 500 million years after the Big Bang. Now say that their timer, the time till they merge, is set for 12 billion years. That means that they will merge 12.5 billion years after the Big Bang. And we'll miss it, right? Not definitely. It depends where this merger happens. If it happens in a galaxy 1.3 billion light years away, then the gravitational waves traveling at the speed of light will just be reaching us now, 13.8 billion years after the Big Bang, and we can detect them. In the vast star-birthing clouds of the early universe, many of the stars formed in binary pairs. If both stars are massive enough to create a black hole when they die, you get a binary black hole pair whose spins are aligned with one another. Other black holes are born by themselves, then start a journey through the vast clusters of young massive stars. As they move through the cluster, they lose energy through interactions with these stars. These interactions are the same as the slingshot maneuvers that space agencies use on their spacecraft to take energy from passing planets. As the black hole loses energy, it will sink towards the heart of the cluster. Here there may be other black holes, and they then capture each other into a binary system. This system will have a more erratic spin alignment than black holes that were born together, and will often merge very quickly. A third type of binary black hole occurs when the black holes are born in binary but very wide apart. Their timers are set for a length of time much longer than the age of the universe, meaning that they cannot be detected by us now. However, if this pair drifts through a star cluster, much in the same way as the single black holes, they will shed energy to the stars around them as they pass, bringing the black holes closer together and meaning that they will merge on a timescale useful to us. So what are these gravitational waves? These ripples in the very fabric of time and space? And how do we detect them? Well, that has been a scientific quest that has spanned a century. Since Einstein first predicted that they would exist in 1916, scientists have tried many different ways of detecting these elusive waves.
I started searching for gravity waves in the early 1970s. In those days, we thought we'll spend a couple of years, we'll build a detector, we'll discover gravitational waves, and then I'll go on to do something else. Little did I know that more than 40 years later, I'd still be a part of the search for gravitational waves. And, of course, now at the point of discovery.
On the 14th of September 2015, a ripple of spacetime passed through the Earth, a gravitational wave, which was detected by the two LIGO detectors. Now, this signal was from two black holes coalescing. This happened over 1.5 billion light years away, yet the detectors here on Earth were still able to measure the signal.
It's really astounding to think that we've witnessed one of the most cataclysmic events in the universe. This is two things 30 times the mass of the Sun crashing into each other. 3 of our suns radiated away in gravitational waves. The effect here on Earth, however, is slightly disappointing. We often listen to the signal from the gravitational wave detectors, and what we hear is a whoop. That's it, 1/10 of a second. But that little whoop is actually a beautiful signal. Slowed down 150 times, it sounds something like this.
To try and understand just how sensitive these detectors are, when this wave passed through the Earth, it would have oscillated the distance between Perth and Sydney on the west and east coast of Australia by 1/1000th of the width of an atom. Now, I stand at about 10 billion atoms tall. So 1/1000th of a 10 billionth of my height over the distance from Perth to Sydney, yet the detectors were able to measure the signal. The signal was detected by the two LIGO interferometers in the US. These detectors house some of the most cutting-edge technology in the world. The most perfect mirrors, the most precise lasers, and the quietest vibration isolators all working together to find these gravitational waves. The research and work that has gone into this technology has been a worldwide effort by numerous scientists. One team of 20 physicists based in Western Australia have been using a smaller scale interferometer to test technologies and solve issues that can then be implemented at the larger LIGO detectors.
Yeah, the laser interferometer consists of two arms. So the laser comes to the beam splitter and split into two and go into two arms. At the end, reflect back and then recombine at the beam splitter. We detected the light at the beam splitter, so that tell you the difference of the two arms. When gravitational wave passing the interferometer, it will stretch one arm and compress another. So the signal as the beam splitter will tell you the difference of these two arms. So when gravitational wave coming, we tell from the signal. We are operating a test facility at Jingjing, Western Australia. The facility is small scale, 80 meters long, but we have the same kind of mirror, laser, and same kind of vibration isolation systems. So we can test the instability and the control strategy of the instability for proper operation of the LIGO.
I had my second baby born 2 weeks before the event, and 4 days before the event, I resumed my program on supercomputers to search for gravitational wave signals. 4 days later, bam, we found it. That's so exciting. My program helped confirm that it's from a particular system, the binary black hole system. My main job is to teach supercomputers to pick up very rare gravitational wave signals buried in huge amount of noise. One of the supercomputers is located at Portsea Supercomputing Centre in Western Australia.
This first event was from a pair of black holes, but there's a lot of other explosions that astronomers have been looking at for many years, such as supernova or gamma ray bursts. Now the exciting thing is that these events also give out gravitational waves. So gravitational waves could be the missing piece in the jigsaw that'll help us find out what's powering some of these events, because it's either unknown or very uncertain. So observing gravitational waves from some of these explosions could give us vital clues to what's powering some of the biggest cosmic explosions that we know.
We are going to have amazing surprises, amazing revelations. That's the promise of gravitational wave astronomy that starts now with the discovery of gravitational waves.
The birth of gravitational wave astronomy is a momentous occasion. Throughout history, with each new type of astronomy, whether optical, radio, microwave, we've learnt amazing new things we've never even imagined before. Now, with the birth of gravitational wave astronomy, who knows? Predictions can be tested. Suddenly, the idea of space-time as a medium able to ripple and curve is a reality. Suddenly, the black holes predicted by Einstein's theory and that astrophysicists have indirectly observed before now can be observed, and they exist, and they're out there everywhere in the universe. Suddenly, we have a whole new way of looking at the universe, and I think we're going to learn amazing things.